And here's another kinematics problem for you guys. Again, chapter 2. So this one is end of chapter problem, number 64. It says Bob is driving the getaway car after the big bank robbery. He's going 50 meters per second when his headlights suddenly reveal a nail strip that the cops have placed across the road 150 meters in front of him. If Bob can stop in time, he can throw the car into reverse and escape. But if he crosses the nail strip, all his tires will go flat and he will be caught. Bob's reaction time before he can hit the brakes is 0.6 seconds, and his car's maximum deceleration is 10 meters per second square. Does Bob stop before or after the nail strip, and by what distance? Okay, so you read the problem one time to get an idea of what it is about. At this point, you're thinking, okay, this is probably a kinematics problem. This is motion in one dimension, so we're thinking about chapter 2 equations for kinematics. So that's where your mind is going. Now you're going to start reading again very carefully, statement by statement, right? And writing down the information that you encounter in terms of symbols, defining symbols, giving them a numerical value, etc. So when you're doing that, you should also be doing a sketch of the situation. Helps in basically all physics problems. So this is a road, that's Bob's car, and he's going at 50 meters per second. And it says that the headlights reveal nail strip that is 150 meters in front of him. So I'm gonna draw some nail looking thing, and I'm gonna set up the distance to be 150 meters. If Bob stops on time, all right. Next part says that we need to read carefully is Bob's reaction time before he can hit the brakes is 0.6 seconds. Bob's reaction time before he can hit the brakes is 0.6 seconds. So what that means is that, as you probably all know, there is a time delay between the moment you see something and the moment your body can move, because it takes a certain amount of time to process the signal coming from your eyes, and it takes a certain amount of time to send the electrical signal down your nerves to activate the corresponding muscles. So that's called the reaction time. So this problem is saying that Bob sees the nail strip, but it takes 0.6 seconds for him to actually step on the brakes. 0.6 seconds. Okay, so I'm going to write that information as a amount of time, delta t. I'm using BB to indicate before braking. So this is the amount of time that has passed before he actually has stepped on the brakes. So this is the amount of time. During this time, he's still moving at 50 meters per second. He has a constant velocity of 50 meters per second during this time. During this time, because he hasn't stepped on the brakes, his acceleration is 0. His velocity is not 0, it's 50, but his acceleration is 0. That just means that the velocity remains constant during this time. All right, we keep reading carefully. There's something talking about the acceleration that the car is going to have. It says that his car's maximum deceleration is 10 meters per second square. Deceleration refers to slowing down, and that we're going to denote it here as a negative acceleration. If we call the going to the right as a positive velocity or acceleration, then going to the left, even though the car is moving to the right, the fact that the car is slowing down means that the acceleration direction is to the left. It's a negative acceleration. That means you're going to be losing velocity at a rate of 10 meters per second every second. That's why he is decelerating. So the acceleration, we write it as a negative 10 meters per second square. And the last part is the one that tells us, well, what we're looking for. What is the question here? So does Bob stop before or after the nail strip? So this question obviously is referring to Bob's final position. Bob's final position is going to tell us whether he stops before the nail strip or after. So we're looking to calculate a delta x, the total distance traveled by Bob's car. That's until Bob stops. So that's going to be the quantity that we focus on calculating. And depending on what number we get, we're going to look at to this number and see whether it's bigger than 150, which means that Bob is going to drive over the nail strip, or if it's less than 150, which means he's going to be able to stop before the nail strip, go in reverse and escape. So this number is going to tell us the answer to that question. And they also ask us to calculate by what distance Bob stops before or after the nail strip. So once we know the distance that it takes Bob to stop, we're going to subtract 150 and see what's the distance between the nail strip and the car once the car has stopped. All right, so that is the plan. Again, we're focusing on calculating the total distance traveled by Bob from the moment Bob sees the nail strip to the moment the car has stopped. Now, the first thing to realize here is that the motion of the car moves in two different ways. The first 0.6 seconds, the car has constant velocity because he hasn't stepped on the brakes yet. So the distance that the car is going to travel, the BB meaning before braking, so delta x BB is the velocity of the car times delta t BB. So that is 50 meters per second times 0.6 seconds. And that gives us the distance traveled during that time. So Bob moves 30 meters before he actually steps on the brake. So I'm gonna sketch that and show the car 30 meters away from the initial location, still moving at 50 meters per second. So now the distance between Bob's car and the nail strip is 120 meters. But now the car is going to be accelerating at minus 10 meters per second. The car is going to slow down and stop, and the distance traveled from the moment the car starts to decelerate to the moment when the car has zero velocity, that distance I'm going to call it delta xb, the distance while braking. This is the distance covered by the car while braking. So during this time interval, the car will have an acceleration of minus 10 meters per second square. Okay, so we need to find that distance traveled by the car during that time. And once we know we have that distance, we add to it 30 meters and then we compare to 150 and see if it's bigger or smaller. So focusing on that, calculating the distance traveled by Bob's car while he's braking. So we're looking for distance. We have the initial velocity, which is 50 meters per second. We have the final velocity, which is 0. And we have the acceleration, which is minus 10. So all of these quantities are known except for the delta xb, which is what we're looking for. So we need to think of a kinematics equation for constant acceleration that involves distance, initial velocity, final velocity, and acceleration, just those variables. So if you look at your 3 kinematics equations for constant acceleration in your formula sheet, you will see that there is one that involves those 4 variables: initial velocity, final velocity, acceleration, and distance. That's the one with the squares. V final square equals V initial square plus 2a delta x. So we're going to just replace. The final velocity is 0. The initial velocity is 50. The acceleration is minus 10. And the distance is what we're looking for. So we're going to get from this equation the distance that it takes the car to stop. So 50 square is 2500. And we'll move that to the other side, change the minus sign on both sides of the equation. We divide by 20, and we get that the distance traveled while braking is 125 meters. Okay, so what that gives us is a total distance traveled by Bob of 155 meters. 30 meters until he brakes, and 125 meters while braking. So 155 is clearly bigger than 150, which means that Bob is going to stop 5 meters past the nail strip, and Bob goes to jail. All right. I hope that helps solving some problems with kinematics in one dimension. I'll see you in the next video.